Good afternoon, everyone. My name is Rez Manning, and I work for the company Allied Scientific Pro. And the title of today's webinar is Nirvascan Spectro-Photometer and the newly introduced cloud service. So I've given this webinar a number of times, and I try to change it up a little bit every time so that it won't be repetitive for those who are attending it multiple times. So this webinar is also being recorded, and the recording will be sent to you in a few days. We also have a Q&A session at the end if you have any questions, or you can type your questions in the chat box, and at the end I'll answer it. My email is also mentioned here, and basically if you have any questions, you can email me later on, and I'll answer the questions. Okay, so we have a long list today, which we may not be able to complete, but we do as much as we can. So the outline of the talk is a difference between near IR and mid IR spectroscopy, and we would also look at the need for a portable near IR spectrometer in various applications. So we would also look at the DLP technology, which is quite different from the linear array detector spectrometers, and examine the pros and cons of that. And then we would introduce you to different types of Nirvascan, different models, diffuse reflectance, transmissive, and fiber optic models. And I'll show you how to record a reference. Then we go into chemometrics, which is required to analyze the NIR data. And we talk about a few case studies, which involves a reflective model. And then I would spend probably about 15-20 minutes talking about the cloud service. And I'll show you how to do the PLS modeling live, basically. And we have added some new features in the cloud that was not there before. So I'll explain those as well, which could be quite useful for those who want to use the cloud. Then there is this deep scan demo app. I'll talk briefly about that. And then we'll go into the case studies. We have a few case studies for the reflective model, and a few case studies for the transmissive model, and also a few case studies for the fiber optic model. We would look into the ISC NIR scan app, and finally I'll show you a few papers published that where they used Nirvascan for the research. So you have a published material as a reference. Okay, so when we look at the near IR spectrum, here you can see it on the right hand side. Let me actually activate the laser pointer. So here you can see the electromagnetic spectrum from cosmic gamma rays all the way to long radio waves. And the near IR is in this region between 780 to 2500 nanometers, right next to the visible region, which we define from 380 to 780 nanometers. And this near IR is also close to mid IR, which is between 2.5 to 25 micron. And then after that is the far IR from 25 micron to 1 millimeter. So when we think in terms of the interaction of light with the material, we have to understand that there are some absorbance of frequencies corresponding to molecular vibrations. So here you can see there are different modes of molecular vibrations, such as stretching, scissoring, rocking, bending, and these vibrations would absorb certain frequencies, which lie in the in the mid IR spectrum. So this is in the mid IR spectrum. So the actual, basically frequency, the fundamental vibration lies in the mid IR spectrum, and you can see it here on the right panel at the right side. It's quite strong and it's quite narrow. So these correspond to uh, vibrations of CO, CH, CN, and NH molecules, and they're quite strong and narrow, as I said before. However, the downside is that the mid IR spectra is quite susceptible to water killing all the other signals. So water would swamp all the other signals. So it's quite difficult to use mid IR for a sample that has too much water in it. And most of the food materials that one needs to analyze has a lot of water in it. Mid IR usually used for petrochemicals, plastics, polymers identification. So for this reason, for the fast quantitative analysis, the near IR is used. And near IR basically uses the overtones and combination bands. So you could have a combination of stretching and bending, for example, or multiple of frequency. It will be first overtone, second overtone, third overtone. And these overtones are 100 times weaker than the fundamental frequency in mid IR, but it allows the user to do a fast measurement with no sample preparation, and is also capable of measuring watery materials. So here is an example of mid IR on the right side and the near IR spectra on the left side for you to see and compare. And you can see here in the mid IR spectra, you see the R and uh, Q bands of different molecules, and they're quite strong emissions or absorption also, and they're quite distinct. However, if you look at the mid IR, the near IR spectra, you see there's quite a jumble here. There's a lot of combination bands and overtones, and they basically overlap on each other from different molecules. So in order to decipher this signal from the near IR, you need to do some analysis, which we call it chemometrics. And I'll get deeply into that during this webinar. So here you can see an H bend, second overtone plus CO stretch, an H in plane bending, CN stretch. So this is like a combination of several bands. You need to be able to decipher this signal. It's not as straightforward as the mid IR. So here we are looking at the absorption band diagram in the near IR. And you can see there is a combination band region, first overtone, second overtone, and third overtone. Starts from the visible, because 700 is in the visible region, but goes all the way to 2500. So our Nirvascan instruments, the standard Nirvascan covers from 900 to 1700 nanometers. And then you also have the extended Nirvascan that covers 1350 to 2150. So the standard Nirvascan mostly covers the second overtone region, which contains water, CH for fat, sugar, oil, all that, and some NH for protein and so on. And the extended Nirvascan mostly covers the first overtone region, which has all of these that I mentioned. Also, some other ones like SH for sulfur that doesn't exist in the second overtone region. So the signal strength is larger for the extended, but the extended instrument is more expensive also because of the choice of the detector and some cooling that may be required. So uh, this basically is a foundation for our measurements, and near IR is a fast, non-destructive technique which requires no sample preparation. It also can be used to identify and to quantify and sort many materials in different industries. And it can be used in process monitoring and also could find the moisture content. We'll get into the examples later. So let's try to explain the digital light processing versus linear detectors. So in normal spectrometers, you have a spectrophotometer has an internal lights. You can see them here, which shines on the material, and the diffuse reflectance is collected and then collimated by a lens and is shown on a diffraction grating. And diffraction grating basically diffracts different wavelengths, and each a portion of the wavelength is received by a element or number of elements in a linear array, as you can see here in the left side diagram. However, for the digital light processing, everything else is the same except that the detector array is replaced by a micromirror array, and also we use a single point in-gas detector. So this micromirror array has several mirrors, and these micro mirrors turn one by one towards the detector. So at this instant that you see on the screen, the green light is shining towards the detector. After that, this mirror turns back, and then the yellow would shine, and then turn back, and then the orange will shine. And the spectrum is built bit by bit. So uh, and then we also use a single point detector instead of an array. So one question is, what is the advantage of using this? And why would you do this? So the number one reason would be that that would reduce the cost of the instrument, because the cost of the micromirror array is less than the detector array. So that would reduce the cost. And then second is that you can use a single point detector, and this way you'll have more throughput. So you could increase your signal to noise ratio and improve the quality of the signal. Also, you can also make patterns. Like in this case, you would measure everything. But here, if you don't want a certain region, let's say you only want to measure from 300 to 400, and sorry, this is from 900 to 1700. So let's say you want to measure from 900 to 1000 and 1600 to 1700, then you can program it so that the mirrors respectively turn, and you would only measure that area. So you don't have to measure everything. So you can make a pattern out of it. Okay, this is a 3D diagram of the instrument, and you can see the two lamps at 45 and 135. There's a slit here, 25 micron by 8.8 millimeter, the diffraction grating, the board, and then the detector. So let's look at different models of Nirvascan. So all of these models work in the range 900 to 1700 nanometers and have a 10 nanometer resolution. So we call these the standard models. So standard referring to 900 to 1700 nanometer range. So the most popular model is the reflective model, which has a window that needs to be placed on top of the material that is measuring. Then you have the transmissive material that comes with a cuvette holder. We don't supply the cuvettes, but you can purchase a glass cuvette from any chemical store or even from Amazon. So we recommend glass cuvettes because there are no absorption features in near IR in 900 to 1700 for glass cuvettes. A plastic disposable cuvettes have some absorption features. And then you have the fiber optic spectrometer. It's not a spectrophotometer because it doesn't have internal lights. I'll show you an application where this uses an external light. And then we also have the three models of extended Nirvascan. So these are the extended fiber optic model, extended reflective, and extended transmissive. So these are in the range 1350 to 2150 nanometers. And the detector is extended in gas, so that's why it's more expensive. And some of these units have some cooling features like fans and things like that. So for this reason, this model is more expensive. Typically, the standard is about $2,000, the reflective one, and this one is about $3,000 to $4,000. The resolution is also typically 12 nanometer at 1530 nanometer. So let's look at the software. What kind of software comes with this? So first of all, I should mention that the software, the PC software, is only available for the Windows. So we don't have an iOS version of the PC software. And basically, you can, when you purchase the instrument, we'll send you a link where you can freely download that. And here is the main window of that. So basically, you connect your instrument with the cable to the computer, and then you run the software, and you will see a green line, green LED turning on here, which shows that the device is connected. So if you pay attention to the top, you see there are three options here: built-in, previous, and new. So the idea of this is if you put this on the built-in, if you select the built-in, then this button turns into scan. So built-in means that the reference is already recorded in the instrument, and that is being used as the reference. So any absorption measurement needs a reference measurement, the I over I naught, the I naught of I over I naught. So that is already measured in the factory. So you can go ahead and directly measure what you want. But the point is that that I naught has been measured with a certain number of certain parameters. So if you want to change those parameters, especially if you want to change the non-time related parameters, then it's much better to record a new reference. So your reference would not be valid if you're changing the parameters. So for this reason, you could put this option, you could choose the option new, and then you will use a spectral lawn reference surface. You put the instrument on top of it and make a reference measurement, and then here you can see it says scan reference. And as soon as you do that, then this would move to previous. So that means it will use the previous reference measurement. Then you can start using your new reference method, your new reference spectrum. These are the graphs that it provides. So you have the reflected intensity, which is what is reflected from the material, the reflectance function, which is I over I naught, and the absorbance, which is log of 1 over R. So for our modeling, basically we always use the absorbance. So that's used in chemometrics. I'll show you how to dig it out from the data. So this already explained how this is measured. The only thing that is extra here for transmittance, instead of 1 over R, use log of 1 over T. Okay, so I was talking about recording a new reference. So as I said, you put this on new, and this is an example of a spectral lawn surface that you can purchase from the company StellarNet. We recommend this. It has 97% diffuse reflectivity, 50 millimeter diameter, and you, in the first step, you measure from this, and then it shows previous, and then you can start measuring from the device. And once you measure your own reference, you can change all the parameters as you like. You can also go to the scan config uh, option or tab here, and then you will see that there are certain scan configurations already in the list. These are already been defined: column 1, Hadamard 1, nitrate. And aside from these, you can also make a new one. So you can just click on new and then define your scan configuration and name it whatever you want, and use it basically. Uh, I should mention that the app does not allow you to record a new reference. So whatever is in the device, whatever reference is in the device is already there. So you cannot do that, but you can still change some of the parameters. If you go to the quick set tab in the app, you can change the time related parameters. So for example, average scans, if you want to use, instead of the default 6, you want to use 100, say, you can do that. And exposure time, I don't really see the need for changing it because you can use different values to improve the signal to noise, but I would try to keep it the same. But if you change the spatial related parameters like scan width or DRes, then this measurement will not be valid because you need to have a new reference for that. You can do the reference and then basically make it replace the reference that already is in the factory, but there's an option for that. But I would try to basically use the app only for changing time related parameters in the quick set, not for spatial or wavelength related parameters. So you notice there was the column and Hadamard. One question is, what is the difference between them? So a column, these are like each of the mirrors. There are different columns. It's like the micromirror array is like a matrix. So in the column, there's only one mirror in each column is turned on to the different position. But in case of Hadamard, there are more than one. So this gets more throughput, basically, the Hadamard, because more number of mirrors are turned toward the detector. So it has a better signal to noise ratio. If you have issues with signal to noise ratio, you can try the Hadamard uh, reference or Hadamard scan configuration. You can also do overlay plots in the PC software, not in the app, but in the PC software if you want to compare, because all these plots are saved, and you can go to the saved basically tab. You can see saved scans over here, and then pull out those different scans that you have done, and then plot them together. So to compare. Okay, so next we have to talk about chemometrics. As I said, you would need to use chemometrics to analyze the signal, the NIR signal, and the chemometrics basically could be divided into two categories. There is one category where you want to sort different material. Okay, like for example, you have plastics type 1, type 2, type 3, up to type 7, and you want to be able to make a measurement and sort them. And for this reason, you have to do either principal component analysis or linear discriminant analysis. And you will see that different if you plot the score plot of the principal component analysis or LDA, different material they group in different sections. So they pile in different sections, and then you can identify different materials. We have done that for plastics, and I have a YouTube video that shows that I've done basically plastic identification by sending the spectra to the cloud, and the cloud would identify, run the model, and send it back to me. So that I'll show later. Or you also, another big application is you want to do quantitative evaluation, which we use partial least square for. So, I mean, you can also use machine learning if you are good with that, but for smaller amount of data, the preferred method is partial least square. So for this, you need to build a calibration model, get a hold of a set of samples, and measure their ingredients using an analytical method, and then basically do the error analysis, apply it to a validation set. I'll get to that later when I describe the cloud. I actually will do it for you so that you see in real time how the PLS modeling is done. Uh, so the Minitab is, for example, one software that could do this kind of analysis, but you need to provide the data in a particular format to it. This is also another uh, you can say method, and it's a webinar by Dr. Heather Brooks, who was part of Chemo Analytics, and they have this software called Unscrambler, which is quite sophisticated for chemometrics analysis. And you can see she has done for wheat all the wavelengths starting from 850 nanometer on the top row in a horizontal row, and then these are all the wheat protein spectra, absorption spectra, so all in the horizontal rows. So you also have in column 1 the protein content for each one. So the protein content has been measured using an analytical method such as HPLC, for example, and is placed on the first column. So you need to establish a relation between the ingredient content and the spectra in the calibration in the PLS model. And then you can do predictions after that. So we have some case studies. We've tried this chemometrics, the PLS model. We have a customer in France that deals with grapes. So he wants to find out what is the bricks contents of the grapes for wine industry. So we got a number of samples from him. So it was 53 spectra that he measured with Nirvascan. You can see, for example, in this set of spectra that there is one outlier here. So it's always useful to take a look at the spectra to see if there is an outlier, something that looks different. They should be all pretty much similar, but maybe slight variations, but they are DC offset with respect to each other. And I'll explain how you can get rid of that in the modeling part. But if something is completely out of shape, then that's probably an outlier, and you need to remove that from your calibration. He had also measured the bricks content using a bricks meter, as you can see here. And so bricks is the number of grams of sucrose contained in 100 ml of water, and uses a refractometer to measure that. So he provided this data to us. And I also should mention that one has to apply the second derivative and the Savitsky-Golay filter. So why second derivative? Because first of all, why derivative? Because you need to get rid of the DC offset, and you need to remove that DC offset. So once you uh, differentiate an expression that has a constant, that would disappear. But why we want to use the second derivative is because the location of the peaks remain the same, as you can see here. But once you do the derivative, you introduce noise. So in order to get rid of noise, you have to apply this some kind of filters, and we tend to use the Savitsky-Golay filter, which uh, basically fits a polynomial. So you would define a number of points. In this case, I think there are like 7 points, and it would fit a polynomial into those 7 points. So this way you will smoothen the curves. So this is the result of our analysis here. You can see the second derivative of the calibration with all the Savitsky-Golay applied. It looks like this. So this is the second derivative, and this is the original spectra, and second derivative plus Savitsky-Golay. And we made a calibration file. You also apply the same Savitsky-Golay to the validation, and then you would do a prediction basically and see how far is your prediction from reality. And here is real predicted. We got RMSE, root mean square error, of 0.77 bricks, which was not all that great, but the calibration curve, as you can see, is missing some points. So around 19 bricks, there are no samples. So in order to get a better result, you need to have basically continuous measurements across. So you need to have samples all the way from, say, 16 to 23, which we didn't have here. Another case study, which we've worked on it more than 1 year now, comes from our customer in Manitoba. So this customer deals with measurement of protein and moisture from wheat, and they have this $20,000 instrument called the grain analyzer, where they put the wheat samples and they measure it, and that will give out a piece of paper saying what is the moisture content and the wheat and the protein content. So this information is quite important for the farmers because the price of wheat depends on the protein, and for storage conditions they need to know the moisture as well. So we provided them the Nirvascan, and they did measurements from initially from 140 wheat kernels. These are the ones from that. And then we also wanted to try it on 15 validation set. But I should mention that this initial approach was not the best approach. If we're going to redo this, we would have to first divide the full spectra, like 140, into two-third and one-third, or 4/5 and 1/5. So 4/5 would be calibration, 1/5 would be validation. Then we establish the error, and then we would apply it on the test samples. But in the first try, when we did it, we just did the calibration on the 140 and applied 15 uh, validation or test set. So what we found out here is the Savitsky-Golay and second derivative spectra. What we found out that moisture gave a good result, RMSE of 0.47, and the protein did not give a good result, 1.73%. Normally, you wanted something to be less than 0.5% to be acceptable. And we were trying to find out what is the reason for that. And uh, throughout last 6 months, we found out there were several reasons, not only one reason, several reasons for it. Uh, so one reason is if you plot the histogram of the number of points in different ranges. In this case, you see the protein. This is protein range, and these are the number of samples. So we don't have an equal number of samples in each range. So the maximum number of samples are between 14.2 to 16.6, something like that. So for this reason, this central region basically. So we get best results if we use this central region. So we don't have enough samples here, and that's why we're not getting good RMSE if we use the full range. So first of all, it's better to plot this histogram and see where the number of samples, and use the region that has the maximum number of samples. The second is that once you, and these are quite important for modeling, for all of you who will be doing modeling, these are our experiences that we are sharing. Uh, the end of the spectra from 900 to 950 and 1650 to 1700 is better not be used. You can see there are these strange features, strange changes happening at the end, and that's for the reason that the responsivity of the detector changes with temperature at around 1700, and this responsivity is quite small at around 900. So to have better modeling, we would try to cut off from 900 to 950 and 1650 to 1700. So these changes you see here, they are real. They're because the sample's ingredient is changing from sample to sample. But these big peaks here, they're not real. And if you include that in the modeling, it may affect the results. The other important issue is that once you do the calibration with one instrument, it's better to do the prediction with the same instrument. So if you have like some kind of calibration model that was used with one instrument, and you use a different Nirvascan to do the measurements, you may not get the good result. Unfortunately, that is the case. We're trying to resolve this issue by making a calibration model which is the average of 5 instruments. But up until we do that, to get good results, do the calibration and prediction with the same Nirvascan. And then also we sent some samples to South Africa to a collaborator who is quite an expert in near-IR analysis, and they had their own South African samples when we sent our Canadian samples. And they found out that the model they made, the South African calibration model, cannot predict the Canadian wheat model because they're different. Basically, they're different types. Their growing conditions, all the agriculture parameters were different. So once they actually combined the two models, the two samples, sorry, the samples from South Africa and Manitoba, then they could make a good predictions of a random number. So if you had, say, 140 and 100, 140 South Africa and 100 Canadian, that's 240. And then you could divide that 240 and say 160 and 80. Then you can validation and calibration. Then you can make good predictions. But if their calibration is from South Africa, validation from Canada, it doesn't do a good job. So taking all of these into account, we've got really good results recently. So we made a calibration model using 80 spectra that gave us a good RMSC. This is only for the model, RMSC of 0.28% for protein. And we applied it to a validation set of 20 spectra, and we got an RMSC of 0.47, and that was quite encouraging. And we also applied it to a test set, and that also gave us RMSC of 0.44. So these are the predictions. You can see the numbers are quite close in most of the cases. So this brings us to the basically end of our case studies. And now I'm going to spend about 15 minutes describing the cloud service and how to do the PLS modeling. So the cloud service is a free service where if you purchase the Nirvascan instrument, you're entitled to use it for 1 year for free. It will ask you to input the serial number of the instrument, so you can't use it just the way it is right now, unless you have an instrument in hand. So you can do uploading spectra and NIR profiles. You could plot NIR profiles. You could do PCA, PLS, LDA modeling. You can make predictions for PLS and also type sorting for LDA, PCA. You can do pre-processing, including second derivative and Savitzky-Golay, and basically all of these are possible. So in order to learn how to do that, so we're just going to go to our Nirva cloud. So let's go to our nirvacloud.ai, and this is the first page that you will see in the nirvacloud.ai. So I'm already logged in here, so I don't need to log in. But if you're a new user, you can go there and register your name and basically log in. So that's all very easy to do. So once you logged in, then you can go to the analysis tab here. Okay, and then they will bring you to this page, which corresponds to upload in the profiles. Okay, so I should mention a few things here, how to prepare the files to upload on the cloud for profiles. Okay, so the first thing is that if you look at a typical Nirvascan data file, here's a typical Nirvascan data file. It looks like this. It has all the scan configurations and all the other parameters at the top, and right at the bottom you have your wavelength, your absorbance, your reference, which is your I naught, and your sample signal, which is your I. So if you divide this one by this one, the I by I naught, you get the reflectance function. And this is log of 1 over R, basically. So what you need to do is you need to select your wavelength. So I've selected this, Control C, and I make a new tab here just to demonstrate. Go to column B1, and then you can use the uh, transpose function of Excel and make this in a horizontal line. Okay, and then you would go to the second one. Let's go to the second one over here. All right, so second line is the absorbance. The second column is the absorbance. So we would copy that. Okay, copy that, Control C, and we would put it in the next row. So here is the transpose. And basically from, let's say you do 100 samples, and you have 100 spectra, so you have to paste all of these 100 in horizontal rows, one after the other, below each other. And the first column, you reserve it for what is the ingredient you want to measure. Is it moisture? Is it protein? If it is protein, you say protein, for example. Here, the heading is quite important. So you say, what is it that you want to measure? And this is the measurement, let's say from HPLC. You don't have to put the percent, but just the number. Okay, so this way you have to build this file, the calibration file and the validation file. So I've already done that for a wheat sample, which I'll show you. So these are the wheat calibration, and you can see we have about, if we go down here, we have about 100 samples there. Okay, and so these are wavelengths, these are the spectra. So, and this is the protein that we are measuring. So this is a proper calibration file, and the naming convention is quite important as well. So the name has three parts. The first part is the material, which is in this case wheat. The second part is the ingredient, which you measure, is protein or moisture. This has to be exactly the same as the title of column A. And the third one is the source, like the company name, in our case ASP, or if there's a field name or there's some other important information that refers to the source of the material, you can put it there. So I also use the word cal in the first part just to make sure that I know this is the calibration. And so G stands for ground. So wheat G cal is the first part, protein dash ASP. And we also have the same thing for validation. So you can see for validation, also I have the same, but we have only 30 spectra. So 100 for calibration and 30 for validation. So once I have that, I would just basically choose these files one by one. So if you choose file, click on this, and you can choose that calibration file. And then here you give it a title. So for calibration, the word cal should be part of the title so that the program knows that this is a calibration profile. And for validation, also VAL should be part of the profile. So once you give this name, you upload it. And I've already done that. So if we go to profiles, so you just go to profiles and you see these two already there. So the name of the profile, we call it test August 2 underscore val. It doesn't have to have an underscore. You can just say whatever name val and whatever name cal. And you can take a look at the spectra right now. So if I click on it, it will plot you the spectra. And you can hide the label, you can show the label, you can look at it at a high resolution, and so on. So these are all the profiles, the test and the calibration and the validation also, less number of spectra. Okay, so here comes the new part that we have already introduced, and we have never talked about that before. So for those of you who are attending this multiple times, this is something new for you. So the idea is that, well, once you want to do the PLS modeling, then how would you know what is the number of components of PLS model and number of Savitsky-Golay filter points that are suitable for this model? So you don't know that. And before we were just using different methods of getting it, but now the cloud could give you that. So you would choose the cal and you would use the val. These are the two files. And then you go to the drop down menu and you say get optimized parameters and then press go. So once you do that, the cloud runs this algorithm that tries different number of components and different Savitsky-Golay and comes up with the one that gives it the lowest RMSC, so the best parameters. So that is 2 and 13. Okay, so at this point you can go to add PLS. You can start building the PLS model. Okay, so here I click on add and I give any title. I can say, for example, test webinar August 3 is the name of this. A number of components, we already know the best one is 2, is already been given to us. And the limits from 950 to 1650. This is the default because we don't want to use the extreme, so we keep it like that. And then we would not use this cal spectrum. We use the cal profile. So which one we want to do? We want to do the calibration. We select the calibration file, and then we say apply SG filter, and number of points 13. We already know 13 is optimized. And these are all the same. They remain the same. Polynomial order, derivative, mirror. These are all the same, so we not touch it. And then we say save. Okay, so this comes here. This is the one that we just generated, which is practically the same as the one that I had done before. Also on August 2 I got 0.94 also. So let me use the one that was before. I was just showing you how this is done, so you can take a look at it. This is your PLS model, and it already comes with the RMSC value of 0.94, and R square is here 0.43, and so on. Now the next step is you need to apply the same SG filter uh, to the validation file too. So you go here, add, press add, and then you call it, say, validation August 3 webinar. Give it a name like that. Window length 3, polynomial 3, mirror, and this cal spectrum you ignore, and then you would use the validation. Okay, and then say save. Save. So give it a little time here to save. All right, so this is what the Savitsky-Golay looks like for the validation. All right, so now we go to the PLS model, and I'm going to use what I already saved on August 2nd. So this is test August 2nd. This is the model. All right, and you want to apply this model to a validation set, so you can go ahead and choose the validation. This is the validation file which has been applied to, I mean, Savitsky Golay was applied to this data, so we choose that test, and then we would go to the bottom and apply the model to predict. And these are all of our predictions. So if you hover over each point, you see it gives you the real and the predicted content. And it will also give you RMSC value. What is the RMSC value? And here at the bottom, you have a score, R square for the model and R square for the prediction. So R square prediction is 0.28, which is pretty good. And these are true versus predicted values. And you can also export these predicted results to an Excel file. So if I click on that, it will just make me an Excel file which has all the parameters. So you can see it has all of these parameters are mentioned here, the predicted and the true value. So once you establish what is the error of your uh, model, then you can have confidence in applying it to other test sets. And in that case, you may not even have the protein. So for a test set, you may not have this column. You can just leave it empty or start from 901 on this one, on A. So this way you can make predictions for something that you don't know. So I hope this description was somehow useful. I tried my best to describe that. I've also recorded a video of what I just said, and we'll send you a YouTube video of that in case you want to do PLS modeling. You can go ahead and do that. Now, I also want to quickly show you the LDA modeling. So let me do that. So for those of you who are not interested in PLS, you want to do sorting, we use LDA models. Okay, so here we have made a model for plastics. So you can see different plastics. We measure from different plastics, and they compile in different areas. Plastic 2, 7, 6, 1, 3. So these are all different plastics. So you can test this model and make identification of any plastic. So for example, if I try in my list here, for example, if I go to sunscreen, I choose that, and then I say apply model to match. So it will put a black square where the model thinks it belongs. So here it was sunscreen. I know it was type 2, and it put it over here in type 2. And we can also try another one. For example, we know for a fact that mustard is type 1. So let's try that. Mustard, and then the plastic, a yellow plastic of mustard is type 1. Apply. And it puts the black one here, which is right next to type 1. So this way you can do identifications of different plastics. And we've made an app that could basically send the spectra directly to the cloud, run the LDA model, identify the plastic, and send the result back. So I can maybe send you a YouTube video of that later. All right, so this was all about the cloud. And we had this demo app before that used to be called Deep Scan, and it had several calibration files and so on. So for example, here I measured the fat content in my arm using the Nirvascan reflective, or you can also measure uh, the bricks content of a mango, and it will also tell you if it is how sweet it is. So because we provide the APK to the customers, they can make the custom-made app based on their needs. Okay, sorry. So here are some more case studies. For example, this polyester content in fabrics. This was provided by a customer from France, and you can even do visual identification of some peaks that exist only in one sample. In sample number 7 there was an extra peak that did not exist in the others, and this could be used the spectra to identify the mixture of polyester and polypropylene and do chemometrics on it. We also did case studies on detection of fake masks. So the 3M mask has the polypropylene, and that has an extra peak that is not observed in the other masks. So you can do detection of fake masks. Now for plastic identification, here is the case right now in most of the industries. Workers, they separate plastics which come on a conveyor belt like shown in here. But in some industries and in the future, for example, a hyperspectral camera could look at different plastics, identify them, and then air come from nozzles would apply to these pieces and throw them in different bins. So there's no need for workers if you use a hyperspectral camera and do the identification. And as I said, we did a app that does that, that does the sorting. So I'm going to send you this. I'm going to send you in chat. Basically, here's the chat, and this is the YouTube video. We don't have time to look at it right now, but you can watch it if you can copy it, and you can watch it to see how this is done. It may be useful for some of you who are not interested in PLS modeling but are interested in sorting. Now, the question is that some customers are interested to make measurements from samples without touching it. So the basically the reflective model has to touch the sample. But if you don't want to do that, we have this light source is called the DRP1. It also has a collecting lens with a focal length of 8 millimeters. So you can connect with the fiber optic to the spectrometer and keep this at the 8 millimeter distance. The spectrometer triggers it and collects the reflected light. And basically this way you can do the measurement at a distance. So for conveyor belt applications, that could also be useful. So this also another video which I will send you over chat. You can watch it if you have time. And this shows you measurement at a distance as well. Okay, I'm going to be quick here. So we don't have time to go through all these applications, but I just want to say that the Nirvascan could be used for detection of viruses in mosquitoes, malaria. We have a collaborator who wants to measure malaria, basically in mosquitoes. And this was another application for the transmissive unit, where a customer sent us some solutions for medical imaging and wanted to know the proportions. And we found out that these samples, they have too much water. So if you use a 1 millimeter thick uh, cuvette, you won't get a signal past 1400. But if you make the cuvette thinner, made it 3 millimeter cuvette, we saw some signals appearing in past 1400. However, another customer sent us some detergent samples, and these detergent samples worked very well with the 1 centimeter cuvette, basically 1 centimeter thick cuvette. We didn't need to make a thin cuvette or buy a thin cuvette, and you could see all the spectra appearing very well. We also had crude oil analysis. This was quite interesting because this is very thick and very viscous. So the customer sent us a 1 millimeter thick cuvette, and basically we were able to get transmission through it. And we found that the more viscous crude oils have very steep rise at the beginning of the absorption spectrum. So these two are basically very viscous, and these samples were not as viscous. Again, using the Nirvascan transmissive, you can use it for detection of viral diseases. For example, detecting flu virus in nasal fluids. This was done by some researchers in the paper, and they basically collected samples from different patients and diluted it 10 times, and they made PCA analysis. In the PCA analysis, the score diagram, they could separate the influenza from non-influenza patients from the samples they collected from their nose. This one was measurement of a spectrum of a light source using the fiber optic model. And you can also use absorption probe to do the measurement. So one absorption probe has two inputs. One is attached to the spectrometer, the other to the fiber optic source, which we can provide. And then the sample goes, the sample, you can say side, goes to the sample and makes the measurement. But this is a two-step process. So you also need to measure the reference first and then the sample. It may be easier to use a reflective model for this kind of measurement. You can also do flow measurements. This is a flow cell where a liquid passes through, and then you can measure the Brix content of that liquid by going perpendicular to the flow. This is basically, these are some videos that show how the apps would work. The apps are available in both uh, iOS and Android. So I'll send you this on the chat and take a look at it. And, and you just connect via the Bluetooth, and it will work very well. How to retrieve the data from the Nirvascan. If you have Android, you can just directly connect via data cable, and it will be in the document folder. If you have iOS, then um, you need to use the iTunes or iTunes software, and you would click on the logo for the phone, and there will be an ISC and IR scan folder where you can find all your CSV files. These are two papers that are in the literature. So basically, one by Australian researchers, they did analysis of the soil and compared Nirvascan performance with other spectrometers, and they found out that Nirvascan could measure the total carbon content very well and the type of the soil. And another paper where they evaluated uh, the freshness of fish, or basically could distinguish between fresh and decomposed fish using Nirvascan. This brings us to the end of the webinar. So in conclusion, we found the reflective model worked really well for different applications. The transmission model demonstrated absorption peaks of some liquids-based solutions such as liquid detergents. The 1 centimeter cuvette for transmission model sometimes swamps the signal past 1400 nanometer, so you need to use a thinner cuvette. We showed the DRP1 external light source that could collect the data at 8 millimeter distance. We showed the use of chemometrics for LDA and PLS analysis, and we demoed the cloud, and we showed the custom app that could be used for plastic sorting. And finally, crude oil spectra was measured using the transmissive model successfully. So we thank you very much for listening, and we'll send you a feedback form. Uh, and if you have any suggestions, I'll be happy to hear your suggestions. So at this point, I would open the floor. If anyone has any questions, please feel free to
So
unmute
I
your. Yeah.
can you hear me? Yes, I had
Yes,
some
please.
questions. So
Yes.
you said a couple of questions. Like if you have, like, I know you showed examples. You can use biological samples also in this, but you mentioned something about the cloud being used. You can use it for 1 year. So what happens after 1 year?
Right. So, after 1 year, there may be a subscription charge, but we
Mm-hmm.
haven't implemented it yet, though. Like so far, we have the cloud for almost like 6 months, and this is something that in the long term may happen. So for
Okay.
now, as long as you have a Nirvascan, you can use it. You don't have to pay anything. But maybe 2 years down the road, if you have, you know, if you still use the cloud, there may be a small subscription charge. But I also should mention another thing. I'm really glad you asked this question. So if you contribute to the data of the cloud, then not only you would not pay anything, you can also may get a royalty payment. Okay, so let's say you have from barley or wheat or any product, any grain, you have some very good spectra, and you're willing to share your spectra to contribute to the cloud library, then you may even be rewarded.
So the all the data that is in the cloud is available to everyone.
Oh, no, that's also another very good question. So some customers, they have they're very particular about their data. They don't want to share their
Right.
data, right?
Right.
So I'm going to show you here, for example, in profiles, right? Once you go upload the profile, you see there is this privacy drop down
Mhm.
menu, right? So if
Right.
you leave it open, then everyone can see it,
Got
but
it.
you can choose private. And if you choose private, you are the only one who can see it.
And all the data which we have generated will be stored in your cloud.
Yes. And yeah, it's completely safe. You can only have access to it yourself.
Okay. So, but does the app also allow some other things which are on the open access to be used?
Like, such as what? Can you give an example?
Like if you have some, like you said, some predictions of protein, this, that, and all, would some of those be also available or no?
Well, let's say if we put a app that uses the model for wheat, okay?
Hmm.
So we could provide you that app. If you request it, we can provide you that app. If the customer who had the samples measured, right, he agrees to be open, then we can provide you that app, and then you can use you could use that data as your calibration, and then make measurements, make predictions.
Okay,
The only
one of
thing
the
that you have to be careful about is that, as I said, you need to be sure that the type of wheat that you're using is similar to the type of wheat in the calibration set.
correct.
Otherwise, you
So,
won't get correct measurements.
so also you said in the cuvette, what is the volume of sample that you need for the liquid samples?
It's not that much, really. So the cuvette is 1 centimeter by 1 centimeter by, say, 5 centimeters, right? The height of it is 5 centimeters, right? So I would say if you have maybe 2 centimeters square, of liquid,
So about 2
then
ml.
yeah, it's
Okay.
enough because the source is at the bottom. If I show you the picture, right, for the transmission model, just a minute. Yeah. So this much liquid I poured in here is way too much, you
Yeah,
see?
okay.
So
Hmm.
it's the source is right at the bottom. So as long as you have maybe 2 centimeters square of this, then it will be enough. So
Also,
even
you
on
had
this picture, yeah.
got I got it. So also you mentioned there was some differences instrument to instrument. Like, is that because the detectors are a little bit different and not completely calibrated? So is that the reason we are not able to reproduce from one instrument to another?
Yeah, there are some minute differences. The calibration could be slightly different. The window material may have slightly different transmittance, the material alignment. There are many factors. I'm not exactly sure why this happens, but I've personally spent months sometimes trying to get a model working, and it was not giving good results. And then I found out that, because I'm using a different instrument than what was done for the measurement for the calibration. So when I used the same instrument, I got much better results. So so that we are working on solving this problem. Though I understand this is an issue, but first of all, if you make your own calibration, then there's no problem because you can use the same device to do validation too, right? But in general, if you're having a big model and you want many people to use it, then we need to make a model by averaging readings from 5 different instruments, and then that model should be able to solve the problem, should be universal.
Okay.
Up until we do that, we cannot guarantee that this would work.
So just one quick fundamental question: when you did the calibration curve for, say, I mean, like some of the wheat, so you have to actually generate the data for from a large data set, and then. But can you use this also for discovery type of work where you are looking for trends that may be used to predict an unknown factor?
Well, if you're using it for discovering something new, right, then the spectrum will probably be different, right? So for
Right.
example, I give you an example. So if you look at just a minute, yeah, when I was just showing the fabrics, right? So all of these are same. All these fabrics, they have the same spectra almost. You see there's a peak around 1382, there's another peak around 1200, right? But
Mhm.
there's only one of them that has a different peak, right? So if you do a PCA model, or if you do a LDA model and then do the score plot, then that will show as a different point outside the pile. You see what I mean?
Yeah.
Like it will be separated from the others, and then you would know there's something different for that.
Right. Got it.
Okay.
Okay. Thank you
Anyone
very
else?
much.
You're welcome.
Also,
Anyone
if you have,
else?
if I have any questions, what is your email? I didn't write that down.
Yes. I'll send it in. So Armani at Allied scientificpro.com. So here's the email. Anyone
And will
else
you be
has any
sending
questions?
this presentation? Will you be sending this recording of this presentation?
Yes, yes, we'll send you. Yes. Within few days
Okay.
you'll get the recording.
Thank you.
Thank you. Anyone else has any questions? If you think of another question, you could always, after watching the video, feel free to email me, and I will be glad to answer your questions. And please fill out the feedback forms too. And please, if you have any suggestions, let us know what your suggestions are. Like, there are 3 questions at the beginning that talk about, whether you like the webinar, whether it was clear, whether it was relevant, and so on. But if you say that you did not like the webinar for any reason, please at least do us the favor and tell us why, and what are the points that you did not like, and how you think we should improve it. So in a previous webinar, I had a person who said did not like, needs to improve, but did not put any reason in the box where it says, well, how you think we should improve it, or what is it that you did not like. So that's kind of unfair to me. So please do that. I would really appreciate it. All right. So if there are no more questions, I thank you again very much for attending the webinar, and I wish you a good afternoon and stay safe. Thank you. Bye.